I look forward to this the whole time. No, this definitely is. So the new topic that we're getting into is particle kinematics and kinetics in a rotating coordinate system. And we haven't done anything in rotating coordinate systems yet. Why does it matter, first of all? And nothing else matters. Not like that. Like, no, I'm not asking a question like that. I'm asking, like, why does it change anything to have a rotating coordinate system? That's why does it even matter? Because Newton's laws require measurements in an inertial coordinate system. And a coordinate system can be non-inertial two different ways. The first one is the origin can be accelerating. Dealing with this one is relatively simple. Oh no, not purposefully, but that brings up my next question, which was how do you deal with this? Yeah. So then we just use the relative motion equations. The acceleration of A relative to the ground is equal to the acceleration of A relative to B plus the acceleration of B relative to ground. So that's not too bad. In the future, when I say it, it will be intentional, but it was unintentional. That's true. And they're still not very good. Do you? Nice. So the second way a coordinate system can be non-inertial is the axes changing orientation. That's rotating. And that's more complicated, trickier. And that's what we're going to do. Let's do it now. Okay, so that's where we are. And if you have both of these, you can just use one of these methods to first do the thing. So you have a coordinate system that's accelerating and rotating. First do the fix for the rotating one, and now you have a coordinate system that's non-rotating, and the origin's accelerating, and then fix that one, and then you're good. So with these two, you can deal with any coordinate system. Okay, so so far we've like everything, the derivatives and everything that we've done of vectors have assumed that the coordinate systems are non-rotating. A vector u, so you can think of it as an x component times a unit vector in the direction of the x-axis plus a y component times a unit vector in the y direction, z component times k. Okay. And in general, a time derivative goes like this. U dot is equal to ux dot times I plus uy dot times j plus uz dot times k. But you have to use the product rule. And so you also get these terms that are ux times the time derivative of that unit vector in the x direction plus uy times j dot plus uz times k dot. And these are the terms, these are what makes it tricky. So remember, like in that first assignment I gave you after the vectors, that was like a refresher on math and talking about vector derivatives and stuff. I said, I said that if you have a non-rotating coordinate system and you take a time derivative of a vector, you just take the time derivatives of the components. That's what this part is, this first part. So this is ux dot, uy dot, uz dot, okay? And if you have a non-rotating coordinate system, u dot is just equal to this because these aren't going anywhere. They don't change in time, and so these are all 0, okay? But if the coordinate system's rotating, then those are non-zero and you have to deal with them. And we don't have right now, we don't have a real clear way. What am I going to say? So these are 0 in a non-rotating coordinate system. But non-zero in a rotating coordinate system. And the tricky thing is, so what are I dot, j dot, and k dot? How do we represent those? And I sort of feel like at the start of this class, I did the sort of intuitive demonstration of the astronaut and that thing spinning around. Does that ring a bell? No? If no one remembers it, I'll do it again. Didn't listen the first time. Yeah. So let's say, okay. Yeah, this is different. Okay, so the math will be about finding expressions for these, for I dot, j dot, k dot. But first, intuitively, what goes wrong if you use Newton's laws in a rotating coordinate system. So, those things like astronaut training, they always do in movies where, yeah. Yeah, that's true. That is the best. So if you want to review this, rent Spies Like Us. Okay, so this thing spins around. Yeah. And I'll put a coordinate system with the x-axis going this way, the y-axis, well, let's have the y-axis coming towards us and the z-axis up. And first think about what a video would look like. So this coordinate system, think of it as a video camera. That's always a good way to think about coordinate systems if you're trying to make sense out of what these measurements mean. Okay, so think of what the video would look like if that coordinate system is fixed. Okay, so first it's not rotating. It's the arm is spinning around and that thing stays right there. Okay, and the audio is like. So there are three frames, and in the first one, you see the person just starting to come in, and in the second one, you see the person going by, and then in the third one, you see that, right? And based on those measurements, you can tell the position, velocity are both changing. And so there's a measured acceleration. The chair has force sensors in it. And so when you compare the force sensors in the chair to the acceleration that's seen in that coordinate system, think of this as like the acceleration that's observed in that coordinate system. Newton's second law holds when the measured forces are compared to the measured accelerations. Okay, but now think of a video where the coordinate system is rotating with the person. Yeah. So if the coordinate system rotates with the arm, then as the person goes around, the x-axis is always looking at the person. The audio is like, oh my God, it's still going. Oh my Lord, turn it off, somebody. And these 3 frames of video look like I just like that drawing so much. Oh no. Yeah. And so now it looks like the position is constant. And so the velocity vector and the acceleration vector are both equal 0. The sensors in the chair still measure the same forces. Right. So the observed forces and the observed accelerations don't satisfy Newton's second law. Hey, Rob. Oh, yeah. By me, probably. So observed forces don't satisfy Newton's second law. On my sabbatical, I taught finite elements there. So I spent a semester over there with, I mean, it's a fun atmosphere. It's a different atmosphere than what I'm used to. So
if you had that option when you were in college?
Well, no, I wouldn't have, I don't think, because I mean, I basically am like a math person, so like that was just never the stuff that I was into, but not because of a quality thing or whatever. It's just like the way they do it at the U is the way I sort of like doing it. But although I know they have had people go right into grad school, but I have heard people say that, yeah, that like the U is more mathy and feels more like getting you ready for grad school or whatever. Okay, so where we are here is, I think I did. So that's sort of just a demonstration of how a rotating coordinate system makes it so that Newton's second law doesn't apply. That's something you can just sort of store in your head for when that question comes up or whatever. So now what we need to do is mathematically how do we deal with I dot, J dot, and K dot. Okay, well, let's think of two coordinate systems. I'll do them in two different greens. So let's say that this is, so we have the idea here is that we have a rotating coordinate system, and we're looking at it at two nearby instants in time. So let's say this is the x-axis, the y-axis at time t, and this is the j-axis at time t. And then some, you know, think of it as like an infinitesimal time later. You have this coordinate system where this is the x-axis at time t plus dt. And this is the j-axis at time t plus dt. And I'm just doing this in 2D, but the same, you can do the same thing in 3D. It's just harder to draw and stuff. The thinking is the same. You have to have all three axes rotating, and yes, you'd have to think about a rotation of the, so the I axis would have a rotation about the y-axis and a rotation about the z-axis. The y-axis would have a rotation about the x and the z, and so on, and you have to deal with all these other things. But you'll just want to just trust me that it works the same, and because this is a lot easier to store in your head. And really, the only reason I'm going through this is something you can sort of store in your head to remind yourself when you get lost on this stuff where it comes from, you know. Okay, so what happens in here? Well, these go through some infinitesimal angle. So I'm going to call that d theta, and both of these are the same because we're in the plane. And we want to calculate this vector and this vector. Okay, so this one is the change in I, and this one is the change in J. Okay, so let's try to come up with a description for these vectors dj and di. If we can do that, then we can just take everything as a ratio over dt, and that'll give us our expression for I dot and j dot. Okay, well, this is, I'm getting a little loose with the math on this, but you have to think of what happens to everything as a limit as this goes to infinitesimal. You know, obviously I drew that as a finite angle, but these all get small. And so, like, even though this, for a finite angle, this isn't a 90-degree angle, as these approach, you know, the same line, that becomes a right angle. And so we can think of this as right angle trigonometry. What's the length of I at t, what's the length of that vector? The length is just 1, right? Because this is a coordinate system, and same with that one. The length stays 1 the whole time. And so the length of, so let's think about di. Whoops, and change this. Those are not, those are not unit vectors. I have those written like they're unit vectors, but obviously those are infinitesimal, so these should just be vectors. Okay, so in order to define that di, we need a magnitude and a direction. The magnitude is going to be 1 times sine of d theta, right? So that's just sine of d theta. And as d theta approaches 0, what does sine of d theta approach? Like this is the small angle approximation. It approaches d theta, remember that? So the smaller that angle d theta is, the closer sine d theta and d theta get to each other. And now what's the direction? Well, that's perpendicular to I, right? So it's in the direction of j. And which j? Is it j at t or j at t plus dt? They're the same, you know. They're infinitesimally far apart, you know what I mean? So the answer is di is equal to d theta times j. Who finds this interesting still? Okay, good. 2 people, that's the best so far. Okay, and now let's do the same thing for j. What? Yeah, perfect. Right, exactly. So dj, what was your question? It would be both of them. You know, as that thing approaches 0 angle. For a finite d theta, it's not perpendicular to either of those two, but for an infinitesimal angle, it's perpendicular to both of them. And dj now is equal to, so let's look at that. We can, again, that's 1 times sine of d theta, which is equal to d theta. And the direction of that vector is negative x direction. So negative I direction. What? Oh. I was just going to write it here and then. This thing hasn't been working recently. Okay, so dj is equal to d theta negative I. radians. Okay, so now take these two things and what we want is, you know, I dot and J dot. Divide both sides of the equation by dt. Really what you'd be doing is using the chain rule, but you can think of it as just dividing both sides by dt. And you get that di is equal to d theta dt times j. And dj, this is dt. These are vectors, so d I dt this is a vector. Dj dt is equal to negative d theta dt times I. Well, I'll just tell you the answer to that at the end, because we're just doing that in the plane. But I just want you to see this pattern that's going to develop here, and then I'm going to just tell you that that pattern holds for the in the three-dimensional case too. Yeah, well, you can go home and do it. Actually, I should have signed that. I won't. You don't have to walk to TCU. It won't hurt my feelings. If nobody goes with me, I'm not going to go, though. I've already been there. I've been there plenty of times. And finally, notice that d theta dt is equal to, we're going to call this capital omega. No, this is the angular velocity of the coordinate system. Nope, not ohms. Okay, so we have, this gives us that di dt is equal to omega j with the unit vector, or I'm being inconsistent here. Yeah, it's not a unit vector, but it's a derivative of a unit vector. I think I always do it as a unit vector. So di dt and dj dt are not unit vectors, but they're time derivatives of those unit vectors. You know what I mean? That's right. So di is this. Dj dt is this. And so you can write that as I guess actually I'm going to go one more step here. So u x times I dot plus u y times j dot. That is, remember, that's what we're trying to get to. Where is it? Okay, so we're doing all this so we can represent this stuff, right? And so now we're finally going to use what we just calculated to figure out what ux I dot plus uy j dot is. And it's equal to the angular velocity vector crossed with the u vector. Or in 3D, ux times I dot plus uy times j dot plus uz times k dot is equal to omega cross u. Okay, so now we know how to, if we know the angular velocity of the coordinate system relative to something that's not rotating, that's our representation of that term with the u components times the axis dot. And then that means that, so you can think of it this way, the final result is that for any vector u, expressed in a rotating coordinate system, u dot is equal to the derivatives of the components plus omega cross u. Another way to think about it, the same thing, but just expressed in different words. U dot is equal to the U dot that's observed in the coordinate system plus omega cross U. Okay, so if you got tired of going through that derivation and you're uninterested in the derivation and you're sure that there's nothing for it to teach you, just start paying attention here and here, okay? This whole derivation was about coming up with those expressions for how to take a time derivative of a vector expressed in a rotating coordinate system. You can think of that as, I mean, it's true in a non-rotating coordinate system too. If you take a time derivative of some vector u in a non-rotating coordinate system, it's equal to the time derivatives of the components. Omega is equal to 0, and so it just reduces to what we're used to. Okay, but what we're going to do next time is using these two equations, this one equation, we're going to take time derivatives of the position vector to get the velocity vector, time derivatives of the velocity vector to get the acceleration vector. And then we'll have these expressions, sort of complicated expressions, that'll let us use Newton's laws when all of our information is coming from a rotating coordinate system. Anybody have any questions right now? Yeah. What? Not necessarily. It's anything. It's kind of amazing that you can come up with something that general. But that says it doesn't matter what you measure. If the thing you measure is a vector, okay, which means that if you took your measurement in a different coordinate system, those two would match up if you applied a rotation matrix. That's what a vector means. So if what you measure is a vector, then do this, and it'll give you the time derivative of that vector as it would be observed in a non-rotating